Forrest is a professor in the graduate school, the old hands of the laboratory. Let's see, I want to guess that you arrived here in Berkeley in 1966?
66, yeah.
1966. And he remains active, maybe as active as he's ever been to this day. So Forrest is going to tell us about the history of the lab. There you go.
Okay. Yeah, this is on. Is this the... okay, great. I wondered why I got chosen to be the speaker on the history of the lab until I found the quotation by Stendhal about what a historian is. What's that? Okay. So I want to explain how the lab grew, who the key personnel were in that growth, and how it is that we've come to the place where we are, in my unbiased opinion, the premier academic institution in the world for the full branch of space science research. How do I change that slide?
You have to use the arrows.
On this guy?
On the keyboard.
Oh, okay. All right. So to set the stage for the eventual approval by the Board of Regents of the Space Science Lab, I want to talk about the period of the 1950s and what was going on in our attempts to launch satellites into space. The United States had two programs. There was the U.S. Army-Navy program called Project Orbiter, which was canceled by Eisenhower in favor of Vanguard. But Vanguard started having troubles in a hurry, and so the Project Orbiter program was restarted and called Explorer 1, called the Explorer program. The first payload, this is interesting to people who spend 10 years now building payloads for space missions. First payload was built in 84 days, surrounded by Vanguard launch failures. And finally, when a Vanguard was launched, Khrushchev derided it as being the grapefruit satellite. And part of his reason for doing that was that the Russian launches were very major rockets and very major, in terms of mass, satellites. And there's a reason for that. It's that the Russian engineers that built their first launch vehicles were told that the weight of an atomic bomb would be huge. And so they had to build a launch vehicle that was compatible with launching what they believed to be the huge weight of their atomic weaponry. And the United States didn't have that problem, but succeeded in failing anyhow. The actual discovery of the radiation belts is credited to Explorer 3, which is not completely fair. The Russians certainly saw the evidence and published in Russian journals evidence of the radiation belts far in advance of Explorer 3, and Explorer 1 was launched with a Geiger tube, as was Explorer 3. It's the same payload. They also saw but didn't understand what they were seeing when they measured the radiation belts. There was a graduate student at Iowa who had been an undergraduate music major, and he decided that he wanted to become a physicist. So he went to Van Allen and started working in his lab, and Van Allen dumped this massive data from Explorer 3 on his desk and told him to understand it. And it was difficult to understand for two reasons. One is they thought they were going to measure the latitude dependence of the cosmic rays with their Geiger tube, and they found counting rates that were huge compared to what they expected from cosmic rays, and so that was a mystery. There was another mystery too, which was that the counting rate in Explorer 3 would go up gradually through the orbit and then suddenly decrease to zero, and no one understood that other than this music major who went out in the lab with a Geiger tube and put large fluxes of X-rays into the Geiger tube and found out it saturates. So he explained the saturation, the zero counts in the Geiger tube is due to saturation, and Van Allen picked this up and the radiation belts became the Van Allen belts. I'm not going to tell you who the graduate student was. You probably know, but if you really need to know badly, I'll tell you later. And then I have, through this talk, I have some quotations like this designed to make a history talk a little slightly more interesting than they typically are. So keep in mind this time frame. We're talking about launches in 1958, and the Space Science Lab, first indications of the lab were in that time frame when Chancellor Seaborg established a committee on space sciences to study the possibility of space research in the Berkeley campus. And in February 1959, the committee presented a report to Seaborg, and it's interesting to look at this timeline. The proposal that they made in February was for $25,000 from the university and $250,000 from NASA. 1 month later, those numbers had doubled, $50,000 from the university and $500,000 from NASA. And when they finally made a proposal to NASA only 2 months later, they had more than doubled again. So there was plenty examples of how programs grow, dating right back from the very beginning. It was not funded. I'll come to why it wasn't funded. Yeah. That's also typical, by the way. Okay. So this was the proposal from the committee to Chancellor Seaborg. Oh, okay. How did I? Okay, is this better for people? Thanks, Steve. This is the proposal that was written to Chancellor Seaborg by the committee that he had formed, and the committee membership is right here. The most distinguished faculty on campus, Otto Struve, was a professor and chairman of astronomy. Melvin Calvin, we already learned, is a Nobel laureate in chemistry, and his name is attached to that of a very famous professor of chemistry. Bill Freder was the professor of physics and the vice president of the university, and on down the list, Edward Tellier and so forth. And they were very impressed by the possibilities of space research, and so was the president of the university, Clark Kerr. So then that was a proposal to Chancellor Seaborg, which resulted in a formal proposal to the Regents for establishing the Space Science Lab. And some information, this is the cover page of the proposal to the Regents, and I like this quote down at the bottom. The budget in that proposal is kind of interesting. So the director of the Space Science Lab, who had not been appointed at that time, and it was Sam Silver appointed the following year, but the budget for 2/3 of his salary was $12,000, and it goes on down the list, and you can see how the university got to this mammoth proposal of $500,000 to run the Space Science Lab. And the Regents approved that formation of the lab with initial budget from state funds of $50,000 and a formal proposal to NASA. And this is the cover page of the formal proposal to NASA, which wasn't funded because the NASA administrator at that time was Keith Glennon, and he was opposed to supporting laboratories, supporting facilities. His policy was to support only specific projects. So that proposal was refused. Then in January 1960, almost a year after the lab was formed, Sam Silver was appointed director, and the lab operations began. This is almost a joke. Began in Leuschner Observatory. And so what I'm going to do is deviate a little bit from the timeline and talk about the buildings that have been the Space Science Lab buildings. So the Leuschner Hall this was a temporary building, and there it is, Space Sciences Lab. It was it was big enough. It was big enough for Sam Silver's office. I was only in there once, and never had a desire to go back. It really was just Sam Silver's office, and I view Sam Silver. Can I go backwards? I don't see how I can go backwards here. It doesn't matter. Well, let me go back a little bit. That's what I thought I'd pushed. No, it's going forward? Well, yeah. I don't know, there, all right, we're far enough back. Thanks. So what I wanted to do was explain this statement down at the bottom. I knew Sam Silver fairly well, and he was very quiet, mild-mannered, easygoing guy, I always thought. until I started reading some of the literature back associated with these very early days of the lab. Turns out he was a very forceful character. He saw that the lab was becoming an administrative center for administrating space research and NASA programs. And he wrote a very strong statement in one of his early documents saying that he didn't want to be the director of a lab that only was an administrative center, that it had to have research facilities. And in my opinion, that's a larger reason behind the university's supporting the various research centers up until the time that we got our final buildings. So we've been there. The second place that we, as a result of Sam's insistence, the Richmond Field Station, which was the old Ford laboratory in Richmond, became the research center for the Space Science Laboratory. And I should say that in those days, the character of the Space Sciences Laboratory was very different than it is today. There weren't, at that time on campus, people very interested in and working on building instruments for space missions, for example, or doing ground-based measurements of things related to space instruments. So the initial program at the lab set up at the Richmond Field Station were these things: study of primates, genesis and maintenance of life, and Carl Sagan was involved in that. He was a postdoc here at the time, and study of mammals. So it was mostly the life sciences that were the topic of research when the Space Science Lab was first formed. So we're coming down the list. We've done Richmond. We're going to do 2119 University Avenue. This is the site that we called the shoe store, and it's remembered fondly by many of us. That's where the lab was when I came to Berkeley in 1966, and it housed mainly Kinsey Anderson and his graduate students' research in space plasma physics, and I think Melvin Calvin had facilities there also. And then Clark Kerr was friends with the then NASA administrator, James Webb, and worked out an arrangement whereby NASA provided the funding to build what we now call the Sam Silver Lab, the westernmost big building up on the hill. And this is the memorandum of understanding between NASA and the University of California that led to the funding for building that building. And this is an important document to those of us who work there today because of this statement up here in the top of the page. Every few years, PTO, Parking and Transportation Office, tries to take away the buses that come up to the Space Science Lab or charge fees for people to ride the buses. And so we have to pull this agreement out every few years, and it says the cost of the road expansion and bus service will be borne by the university. And that's the way we should have said parking also should be borne by the university. But we weren't smart enough. At any rate, we don't pay for the bus service, and we're never going to, and it's going to be there in perpetuity just because of that one sentence. The building was then completed in 1966, and this is the dedication of the building in October of 1966. And I think you may recognize all the people. This is Sam Silver. This was George Miller Sr., the congressman from our area. And this is not Stuart Bale, in spite of the fact that it looks like it's Roger Hines. And the speaker is James Webb, and hiding behind him is Clark Kerr. As an aside, the story of Clark Kerr is interesting. He's now considered to be some kind of a hero to the university, and the place we're going to eat dinner tonight is a rather large facility that's named in his honor, but his demise at the university was sudden and unfortunate because he was the chancellor and president of the university at a time when of the House Un-American Activities Committee, the McCarthy era. And the state of California duplicated what Congress was doing by having a state Un-American Activities Committee, and they hounded this poor man, such that within a day or two of Ronald Reagan being elected governor, he fired Clark Kerr. So this was a joke. I thought when I came to the Space Science Lab, because there was common discussion about, gee, we ought to build a aerial tramway from the campus up to the Space Science Lab, and we ought to put a restaurant on the top of the Space Science Lab, and that'll fund our research. And I always thought that was pretty funny until I found this old article looking through the literature. It was a serious proposal, and the idea was actually proposed by a private company that said the university could run it on the week, and they would run it on the weekends for profit. So it was given serious study, as you can find out by reading this thing, but it did never happen, so we have to go to NASA for our funding. So then the lab established a facility also in the Marchant building down at the bottom towards the bottom of University Avenue, and Tom Jukes and Space Physiology Group were in that facility. And then finally, the addition to the Space Science Lab, which is the second big building, the easternmost building, was approved as a result of Garamendi legislation. Garamendi at that time was in the state legislature. He's now running for, I think, a congressman to replace, okay. But so he's been around a long time, almost as long as Brown in Oakland. But he made a proposal which the legislature passed for raising bond funds to build research facilities. These were not teaching facilities, but research facilities on the UC campuses. And there was only going to be one building selected at each campus, and we proposed the addition to the Space Science Lab, which was selected. So it was completed in May 1998, and the cost of the bonds are being repaid by increased overhead that comes from the use of the building for research. And every year till now, we've exceeded the annual payment, and we're not, this is constructive bookkeeping on the part of campus, we're not credited for the excess overhead, so every year we have this bill to pay. But the building is roughly half paid for by now. So where am I at? I'm way down here. I want to talk about the core grant proposal, which was really important to the establishment and to the direction of the Space Science Lab. This was a proposal made to NASA and awarded by NASA for a total period that ended up being about 10 years and being a large fraction of $1 million. I think it grew to a large fraction of $1 million per year, but I'm not positive that. It immediately, starting in 1961, supported about 50 faculty, 90 graduate students, and some 50 projects. And as I said earlier, these projects were this is that proposal. These projects were in the life sciences, physiology, and sociology. And James Webb, the administrator at NASA at the time, was very much interested in having social sciences study how physical sciences work together and whether there's a way to bring that method of collaboration into a larger audience. So in the first 10 years of the lab during the period of this core grant, there were a large number of the sociology faculty wandering around listening to what we said and writing reports on it. And this is one example of how that core money was spent in the early years. So there are on this page 6 talks giving at a seminar on a particular day in 1967, and you see almost none of them are related to the mission of the lab right now. There's chemical evolution and social significance of technological advance and ethics of large systems, and only one talk which is related to what the lab does today by Harold Weaver. This is the personnel associated with the lab as a function of time. And let's look at these purple squares. That's the faculty times 10. So over the last years, the number of faculty has been roughly around 20 associated with the lab. But there was this huge bump in the beginning associated with the core grant and associated with people from the life sciences, physiology, and sociology that were funded by the core grant and that left their connection with the lab when the core grant ended. And so that explains that bump. it also built up the total personnel in the lab to a number that's been rather constant since, something over 300 or 350 people. So the lab size today is, and has been for a long time, about 350 people. The faculty associated with the lab recently has been decreasing a little bit, but is somewhere in the range of 20 faculty members, of which less than half are physically located in the Space Science Lab, but all of which perform their research with funding that comes through the lab. Number of graduate students has averaged 40 or 30 per year. And I like this particular quote at the bottom. Me. Now, that quote actually was referred to mathematics departments, so I changed it a little bit because after all, we're guests here today. We can't do that. Okay, so I'm way down here. The first plasma instruments were flown in satellite by Anderson's group, and I'll talk about that a little bit more, the new buildings. Anderson became the director of the lab in 1970, and one of the two significant things that I think Kinsey did, which really formed the direction and future of the lab, was the Senior Fellow Program. And I want to talk about that. This blank page is the proposal that the Space Science Lab made under Kinsey's direction to campus for a Senior Fellow Program. At the time, our professional researchers in the lab had to get exceptional PI status if they wanted to be a PI of a mission. And mostly the PI status exceptions went through the campus budget committee and were mostly allowed, but sometimes not allowed. And the whole process was cumbersome and was limiting. So Kinsey suggested that we form a group of scientists called Senior Fellows who acquire PI status as a result of being elected Senior Fellows and who go through the same vetting procedure that faculty members go through in terms of searches and letters of recommendation and evaluations. And Kinsey had the right idea. He wanted the Space Science Lab to grow into what it's since grown into, and he argued that the lab can't do that with a relatively small number of faculty members. We need the support staff because of the nature of the research that goes on at the Space Science Lab. We need a support staff of professional researchers who have PI status. I see this as being one of the two things that really shaped the formation of the lab in the following years. There have been a total of 43 senior fellows so far, and here's their list. 11, there were 8 initially, I think, and then more added since. And of the 43 senior fellows, more than 11, some of these people have question marks by their name, and I'm not sure what their current status is, but at least 11 of the 43 have current faculty positions and senior positions at many universities. And we've managed to keep 19 of these people at the Space Science Lab who are currently senior fellows and performing research. This is the annual expenditures of the Space Sciences Lab as a function of time. At the very beginning, we were spending a few $1 million. This was mostly the core grant. And with time, the funding rate has grown to be an exponential. And I derive great solace from this because I can see that only 2 or 3 more e-folding times will be able to support the whole university, which is the origin of that comment.
What's the e-folding time?
It's 17 years is the e-folding time. So, the 100th anniversary, I'll come back and tell you how we did. Okay. This is the Space Science Lab expenditures and overhead as a function of time. As compared to the total University of California, Berkeley campus overhead from all federal sources, and not counting LBNL, which is not included in this calculation. So over the decade of the 2000s, the total overhead paid to UCB from federal funds and sources was 400 and something million, and more than 10% of that was paid by the Space Science Lab. An additional comment, meant for our Vice Chancellor, is that our return on the investment is only about 15%. He heard. Okay. We're currently managing a total of about 200 research programs, certainly the majority coming from NASA and some coming from the NSF. These are the PhDs that have been granted for research through the Space Sciences Lab. And there are 242 names on this list, and many of you can, if you really look hard, can probably find your own names. And these statistics are poor before 1968 because we just didn't have good records, and after 1998 because that's the year that we had to quit, that we were able to quit making annual reports of statistics such as this. So we have an enviable record of having produced certainly more than 250 PhDs in our 50 years of existence. And if you look at the names closely, you'll find them spread out at the best, being the leaders at the best universities in the country. We have built instruments that have been flown on 75 spacecraft that are listed here. The ones with the double stars, such as CHIPS or Themis, are programs where the PI was at Berkeley and managed the program. So it's a Berkeley program, although we subcontracted things like fabrication of the spacecraft bodies. Those were programs run by Berkeley. And let me go back to the very beginning. You can see that in the early 60s, the instruments flown from Berkeley were Kinsey Anderson's research group, who flew on some 6 or 8 missions before anybody else got into the business. And this was also extremely important to the formation and development of the lab for 2 reasons. One, Kinsey had a lot of really good graduate students who went through that program and have gone off to be leaders at other universities and in many cases come back here in retirement, for which we're thankful. But more than just having trained excellent students, Kinsey produced a group of engineers, electrical engineers, mechanical engineers, software people, that became the core of the very excellent engineering staff that we have at the Space Science Lab today. So Kinsey's to be thanked on many levels for his pioneering work at the very beginning of our lab. The first planetary experiment was done by George Pimentel's group on Mariner Mars, and a prototype of the instruments out in the lobby. You can go out and take a look at it later on. There are many other experiments, spacecraft, that are interesting here, and I'll just mention them. There are a lot of experiments in this area by Buford Price's group that look, for example, at plastic tracks in glass on Apollo 16 and several of those. And then Stu Boyer came into the act with experiments in the EUV and in the X-ray astronomy. I think all of these things that I'm summarizing will be discussed in greater detail by other speakers. The one I like the best is S33, which was an auroral payload in which we discovered the auroral acceleration region, which is a region at relatively low altitudes in which electrons get accelerated to the energies that are observed and precipitated into the aurora to make the visible light that's the aurora. You can go down this list, and Giotto was an ESA experiment that flew by Halley's Comet. COBE is a Nobel Prize-winning experiment of George Smoot. What else? RESI is an experiment currently in orbit. It's doing imaging in gamma rays and X-rays of flares on the sun. And I think it's this Bob Lynn's experiment. I'm sure he'll talk about it. But if you stop to think about it for a minute, how do you image gamma rays? Bob Lynn is going to tell us how. Then the last one that I'll talk, let me talk about the last couple. The COS instrument in the Hubble replacement mission was just replaced 2 or 3 months ago. That was built by Ozzie Sigmund's group here at the lab. And the Planck experiment, which is a very sophisticated 3-degree black body experiment payload built by ESA, George Smoot's working with that. The one I want to mention is the Themis spacecraft. This was a 5 spacecraft mission. So this is one of the very few pictures that you'll ever see with 5 spacecraft sitting in the same room. And they were all built at Berkeley, again, with subcontracts for their fabrication, but they contain almost entirely Berkeley instrumentation. They were launched 2.5 years ago, was it? I think that's right. Huh? Yeah, 2.5 years ago. They've been the idea was that they would be in orbit such that every 5 days they would line up in a radial string down the tail of the Earth and do a radial measurement of the acceleration of charged particles associated with magnetic field reconnection in the Earth's tail. They've completed that instrument. There have been no failures of anything on the spacecraft. It's totally remarkable. And 2 of these are now on their way to the moon because they were in orbits that would undergo long shadows, and they would have died in those long shadow orbits. And with NASA's approval, we're now slowly taking them out to go into lunar orbit. We didn't only do satellite. Man, how am I doing? Am I wasting a lot of time here? 5 minutes. Okay. We not only did satellite measurements, we did ground-based balloon and rocket measurements, and they've been equally important for training of students, for example. In the very first ground-based measurement were measurements on lunar sample returns, and those were done by Buford Price and John Reynolds and I think Melvin Calvin's group. SETI has had a long experience and never found any living examples, but we'll hear a talk on SETI, a very, very interesting ground-based. The Keck telescope, we'll hear a talk from Jerry Nelson on that. A lot of ground-based measurements. The balloons and the rockets were really the training program for some of our scientists and for the development of the instrumentation that's now flying on satellites. We mainly had a rocket program in the 70s. I think I won't spend time on the rest of this, and a lot of rocket programs. We have several measurement payloads currently being built. Barrel and GRIPS are balloon measurements. The rest are satellite measurements. MAVEN, for example, is going to study Mars' atmosphere and volatile evolution. Cinema is an interesting spacecraft. It's being built here. It's Bob Lynn's the PI. It's being built. It's a CubeSat. I said microsatellite, but people don't like that. They like the term CubeSat better. It's a 10-pound spacecraft, of which there have been several launched, but they've all been sort of engineering models to test out the engineering capabilities on a 10-pound spacecraft. This one will actually do good science. And it's interesting because it's easily conceivable that one could launch 50 or 100 of these things because they're so lightweight and relatively inexpensive. So one can imagine a constellation of these things, for example, throughout the entire magnetosphere, studying the time evolution over the entire space of things like substorms and magnetic field reconnection and so forth. We have several proposed satellite missions that are at various stages of development, and we've had a few failures. And you should notice here that none of these failures are associated with instruments from the Berkeley group. They're all spacecraft failures or some kind of launch failures, or in the case of Mars Polar Orbiter, it crashed into the moon and our marvelous microphone experiment got crushed. So this is the sentence that I'm most proud of here. To my knowledge, there have been no failures of any Berkeley instruments on launch, and all instruments have been delivered within, I say expanded schedules because all spacecraft missions slip, and within the expanded cost. So sliding over the word expanded for a while, every instrument we ever built, well, we weren't the cause of the expansions in most cases. In some cases, we may have been. But our track record is in fact really remarkable. We built this very large number of instruments. None of them have suffered infinite mortality. Of course, they all get old with time due to radiation damage and so forth. But I think our track record probably can't be equaled by anything, by anybody. And so my final comment is we're pretty great. Thank you.
Thanks, Forrest. That was great. Do we have time for a couple questions? If anyone
Yeah, I'm not sure about answers, but we have questions.
Does anyone have a
Question or comment? Did I do anything wrong? Good. There's no old people here.
Well, there's a history of the physics department that's in a book form, I guess, which I found very interesting. Just hoping that you would put out some sort of publication that will have this history.
Thank you for that comment. It's our intention to put every PowerPoint presentation on a website and send out email to everybody so that you can get these presentations. We're also tape recording every talk, and people who are giving talks who are willing to be tape recorded and willing to have their presentation put on a website have to sign a legal document here. And people who are giving talks that don't wish to do that, just let us know and we won't do that. But the hope is that for the vast majority, maybe all of the talks, you'll find them on our website. Thank you for the question.
I'd like to make a comment. I love the talk, and my areas are really fast and sounding rockets. I just want to make a comment on the sounding rockets. We had to go through quickly, but I think it's really a great thing that Berkeley has done this fall program, such as sounding rockets, because there's the instruments got developed, and I think like the top, everything on fast came from sounding rockets. Not only the top hats, but the electric fields and things like that. So the rocket program, I think, is really good.
Yeah, that was a comment from Rob Pfaff, who at Goddard is head of the rocket program. But what he says is true anyhow. It doesn't matter. It's really the case that for many, many years, our students earn their PhDs by building instruments for rockets and satellites, for rockets and balloons. And that was very important in student training. These days on satellites, it's very hard to get student involvement. And we should be trying to maintain an ongoing rocket and balloon program for that reason. Thank you, Rob.
And we are.
And we are. Oh, yeah, that's the other point. And we are.
All right. Any more comments or questions? Okay, thanks.